By the way, Freidun, when was the last time you have been to Israel?
Last time.
Was it to Steve Gelbart's conference?
Probably. I was there for an AMS before that, and I have been there several times. So I think it was probably his conference. So this will be the next one. That's it.
Yeah. Very good. So the YouTube works. All right. Are we ready to start?
Okay, sure.
Okay. So I'm very glad to welcome Freidun Shahidi and announce his talk on multiplicativity of gamma factors and Fourier transforms via Braverman-Kazhdan program. Please.
Thank you very much for inviting me to talk. As we discussed, this is probably the first time after Steve's birthday that I've been here, and it's a pleasure to be here. And my talk is going to be the first Zoom presentation of me, so good luck with me. So let's move on. This is a joint work with my student, William Sokurski. I mean, the last part of the talk will be going over some of his results. And it is intended to just be some basic review of the Braverman-Kazhdan, which Engo pursued and Laforgue has done it in a different way. And finally, stating the conditions needed for multiplicativity and doing the, I'm not going to go to proof, is similar to what you can do in that Jacquet and Goleman did, but I will go over some of the basic facts about the subject. So let's start with the setup. It's the p-adic field. I mean, F will take a characteristic 0, so finite extension of QP. G is a connected reductive group. I'll take a split for simplicity. Already some work is done, I mean, in some of the papers of Engo, to extend it to a general reductive group. And references are the Goleman-Jacquet's book, 2 papers of Braverman-Kazhdan, 1991 and I think 2010 and 2001. The first one on normalization of intertwining operators, and the second one gamma factors. Those are foundational papers. 2 papers of our Engo. The last one is in the volume for Cytos, and some of the papers by Laforgue. So the goal is to generalize what Goleman and Jacquet did, setting up an integral representation for the standard L function of GLN and trying to get the properties of the L function out of that. It is some uniqueness involved, and that's basically a consequence of Schur's lemma. And we want to generalize it to any, group and any representation of the L group. So let me first quickly go to the situation of the Goleman-Jacquet zeta integral. This is just defined by a function phi, a matrix coefficient f, and a complex variable s. The function phi is in the standard Schwartz space of GLN. So this is CC infinity of all the n by n matrices with entries in F. F of x is a matrix coefficient, so it's just pi of x, v, and v tilde. And so v is in pi and v tilde is in pi tilde. And this is for an irreducible admissible representation of pi, anyone. And s is, of course, a complex number. A standard Fourier transform, as we know, is just given by the integral of phi of y. Psi is an additive character, non-trivial additive character. And so it's a phi of y, psi of trace of xy dy, and n of f. And this is just given basically by a kernel, as I will discuss now. F check of, let me first of all, I'll get into this kernel. But f check of g is f of g inverse, which is a matrix coefficient of pi tilde. And then z has the property, let me just go, you see the z again, let's go back. Z satisfies a functional equation. This is there exists a scalar function gamma standard of pi and s, so that z of phi check f roof 1 minus s plus n minus 1 over 2 is equal to gamma times the other one now with f and phi. And this has to be true for all phi and all f. The fact that such a scalar exists is a consequence of pi being irreducible and a consequence of the Schur's lemma. There is this important shift. The shift n-1/2 is really, I mean, you can see that it is given by this pairing. A of GLN, this is the notation of NGO. I'm going to use that notation, is 1/2 of the sum of the positive roots. You fix the, Borel subgroup and its unipotent radical. And lambda standard is the highest weight of the standard representation, is just 1, 0, 0, 0. And this is necessary to get the right gamma function, right L function and gamma factor. For example, when you put phi, which is the characteristic function of Mn of O, in this, you will end up getting exactly the standard L function, not a shift of it or anything. So you need to correct it by that. And this function, psi of trace times determinant to the s plus n-1/2, we denote it by ks of standard. So this is the kernel. So when you convolve this with this matrix coefficient f, by the virtue of the Schur's lemma, it's going to give you this gamma factor, gamma standard at pi and s. Now, let me go back and tell you what is the program. We need to replace a couple of objects in this. We need a Schwartz space. So, generalization of Braverman-Kazhdan is just to do everything which works for GLN in general for any row and any group G and any row. There will be some condition on, to get it on the nose, the group G must have some special properties, but that's fairly general. Now, so you need a space of Schwartz function, something that replaces that Mn of f, and functions on CC infinity of CC of Mn of f. And what it does, it basically extends the operation from, it is a subspace in C infinity of G, and it incorporates this data rho and the corresponding Fourier coefficient, Fourier transform K rho. Now you want these things to be defined so that you get the right L function and gamma factor. Let me go back to. So what we really need is, in a general situation, let's call it K nu, we need the integral function, the integral kernel. We want it to be int G invariant. So under conjugation, we want it to not change. And if you notice this kernel that we have for this kernel psi of this one, psi of trace times determinant of s n-1 is invariant under conjugation, just for the reason that both trace and determinant are invariant under conjugation. Now, we want that to happen. Then the way we want to define, we will define our Schwartz space is that we assume we have this f nu, how it acts on smooth functions of compact support, and we add them. This is how Braverman and Kazhdan and cases of S, Schwartz functions in their cases have shown up. The one that they very clearly mentioned is the case of the doubling of the Piotetsky-Realis that I will talk about later. And this K nu should be essentially of compact support, meaning when you convolve it with the function of compact support, it gives you a function of compact support. And again, by the virtue of the Schur's lemma, we should have that K nu convolved with pi, mainly means matrix coefficient of pi, ends up giving off this scalar. Now, if you have this scalar, there are machinery that can give you the L function, but of course we want the L function to be a GCD. And that's what happens. Now, in the general case, we have an embedding of GLNF into Mn of f. What it does, it sits in, it gives you a space of smooth functions, and it will be an extension of these, of these functions in here. It will be all those functions, the image will be all those functions which will have a compact support in Mn of f. Now, general case, what we do, you really need a variety M, and what it does, and you have an embedding of G into M densely, and it extends the multiplication of G to M. So M becomes will have a multiplication, it will be an associative ring, so it's a semigroup. And this will be normal. You want the embedding to be normal. You can always produce this, as I will explain later. This data will determine this monoid. We call this object, this M, a monoid attached to rho. There are several constructions of this. I'll discuss one of them, which is helpful to our purpose. And an example of these are, I mean, the cases on ramified setting. I mean, if these things are going to give us anything, there should be a basic function. There should be, I think Sakalaridis gave this name to it, a function that when you plug in there, you get the L function on the nose. In the case of GLN, it's just M, characteristic function of Mn of O. And here you want it to be supported in M rho of OF. I mean, M rho is a variety defined over F. So you want it to be, I mean, in the case of unramified, M rho of OF makes sense. You want it to be supported there, and you want a multiplication on both sides by K. K is a maximal compact. Of course, you want it to be hyperspecial. It will be invariant under that. This variety M rho is outside the case of GLN and standard is always singular. You will always have some problems with the singularities. And these functions are the Schwartz functions are not going to be locally constant in any neighborhood of a singular point. Now, to make the thing work, to build this construction, we need to make an assumption on G. We will assume it has a determinant, just like GLN. GLN has a determinant. We'll assume some object like determinant exists for these groups. So we'll assume that we want to do the problem for the setting of an arbitrary finite dimensional representation of G check. I mean, we are assuming the group split, so LG would be just G check, and the space of representation V sub rho. So rho from G check to GL of V rho is the representation. Now we will assume that G has non-trivial character. So this means, of course, a morphism from G to GM, so that if we dualize this, so we get a map from C star to G check, and compose that with rho, we compose the new check with rho, we end up sending Z, a scalar, to Z times identity in GL of V rho. Now, this basically means that a pairing between nu and omega, I mean, omega being any weight, is equal to 1. We just do with that, look at it, Z to the power nu and omega is equal to omega evaluating, if you want, you can assume it is W, evaluated that new check of Z, but that's rho evaluated that new check of Z, and with this assumption, it is Z. So nu and omega becomes 1. So it is both, I mean, dominant and it is integral. So this nu is a very important object, because with this nu we can build a structure, build this variety monoid M rho. Now, next what we do, we're going to restrict this rho to the T check, and that will give us the weights of this representation. So it would be a sum over the lambda in W rho, and W rho are all the weights of rho. And we let X star of T to be the co-characters. So this is, we denoted by lambda, this is Hom of GM into T, set of co-characters, or in said other word, the characters of T check. And you can, when you start thinking of characters of the T check, then you can think of the highest weight, which would be a character of T check, and build it on that. Now, finally, we take the space generated by, I mean, vector space by this lambda, and we let C of rho to denote the cone in lambda R generated by the convex span of all these weights. Now, finally, we assume, remember, we assume that we have a determinant function for our group G. This allows us to conclude that C of rho is strictly convex, meaning that it doesn't contain any, this convex cone doesn't have any line in it. Now, this already rules out SL2. I mean, you can do it for semi-simple groups, but you can do it for reductive groups. With the reductive groups having that determinant, you can do it. Determinant you can always produce for a reductive group. Now, let me define two cones. One of them is this convex cone intersected with the co-characters, sigma, and its dual would be dual of C of rho intersected with the dual of X star, I mean, the characters of T. Now, this is the rational dual cone, and then of course it's dual. So sigma and let me just sigma and sigma check are dual to each other, and let's F sigma check be the semi-group algebra of sigma check. Now this will play a role in the character group of the monoid that we're going to now define. So our first purpose is to define a monoid for T itself. The monoid would be a toric variety. Now I'm going to get into that. Now let me look at F of sigma check. That is the ring, the polynomial ring of sigma check generated by F. And this is, of course, contained in F of X door of T by the definition. This, if you dualize this, so if you take a spec of F of sigma check, that will define for you a affine variety and T of rho, and T will be embedded in there. So this is really a toric variety situation. You have an affine variety with a torus embedded in it. Now, this is the first step in building this monoid that we're going to be talking about. Now, this M rho of T is the unique normal toric variety, toric by the meaning that the torus is embedded into it, which is characterized by the following property. And this is very important. A co-character from GM to T, and respectively a character from T to GM, extends to A1. Now, A1 is the closure of, so it's a affine line to this variety M rho of T, the similarly character going from M rho of T to A1, if and only if this character lies in sigma. Remember that how these things were defined. The character and co-characters are inside sigma check and sigma. So if it is in there, it extends. And only using these, we can really build these objects. Now, building of M rho, the monoid that we want to replace that Mn of F, that will give us the space and where the Schwartz functions are going to live, is characterized by those rational representations of G that extend to M rho. Now, this basically says that if we take lambda in X star of T, a character of T, then irreducible rational representation mu lambda with the highest bit lambda extend to M rho, if and only if lambda sits inside this sigma check. Okay, so remember X star of T will be corresponding to sigma check, and the co-characters X lower star of T corresponds to the sigma itself. So in a way, characters of T check correspond to sigma. Now, let me remind you how this thing is done. We have this while group of WGT. It acts on X star of T, and it acts on sigma check. Now, let's assume lambda to be a dominant and integral character. All right, and then this should be X star anyway, the way we have been writing. So this really, you want it to be inside sigma check, and then we take lambda and restrict it to T derive. Usually the highest weight representations are defined for the semi-simple groups, but you can extend it in a natural way. I'm going to explain how you can do it. So you take this lambda restricted to T derive gives you a representation of G derive, the irreducible representation of G derive, mu naught of lambda, and then T derive, which is intersection of T and this, and it will be of highest weight lambda restricted to T derive. Now, this representation we restrict it to the center of the group intersected G drive, and that will be equal to the restriction of lambda to the center's intersection G drive. And then we can extend mu naught lambda to an irreducible rational representation of the G itself. Now you will write G as in the standard way we do, and we let mu lambda be mu nu lambda times the restriction of lambda to the center. This we call the representation of highest weight lambda. Now we want to construct this variety M rho, this monoid M rho. We choose among these highest weights lambda. These are all, integral and dominant characters, and we choose a bunch of them from S of them, so that if we let W act on them, and and they're all going to sit inside sigma check. So if we take the union of these things, this union will generate sigma check. Now, let me take mu lambda I and v lambda I to be the representation attached to lambda I, set mu equal to sum of these representations and v equal to the sum of the spaces of the representation. Among these representations, nu will be one of them. And remember, nu was both, integral and dominant. So let me assume lambda 1 is nu. Then we define M1 to be, we will go through this representation. We're going to go into endomorphisms of V. We find the image of G. We take its closure in the endomorphism of V. Now, this may not be a normal variety, but we can normalize it. And we call that M. The normalization would be M. So that would be how you will this. And this is the construction that Renner gives us. It agrees with parabolic induction in a very natural way. And there is also a construction by Weinberg, but they are similar, and there's a lot of work done in any characteristic in this. Now, let me look at the example of the symmetric cube. Basically, it's easier to take the add cube. That was a funny name. I gave it to you in one of my papers. So that's sim cube times the inverse of the determinant. Let's look at this is a 4-dimensional of GL2C. It will have weights. Remember, x and y is going to go to x squared, y inverse x, y, and x inverse y squared. So the diagonal element goes. So the weights are going to be 2 minus 1, 1, 0, 0, 1, and minus 1, 2. And the C of rho, the cone generated by this will be generated by 2, minus 1, and minus 1 and 2. I'll show you the picture in a second. So sigma, if you look at this thing, it's clear that the convex span of these things is generated by 2 and minus 1. Now, I'll go back to that page again in a minute. And the sigma rho check is generated by 2 and 1, and 1 and 2. So sigma is the semigroup generated by W rho, and sigma check is generated by these numbers 2, 1, these elements 2, 1, 1, 1, and 1, 2. Let's look at the picture. That says a lot more than what I have said. So this is the sigma is generated by 2, 1, minus 1, 2 minus 1 and minus 1 and 2. And this is sigma is generated by 2, 1, 1, 1, and 1, 2. And then f of sigma check is going to be equal to, if you look at the sigma check is basically given by these elements x squared y, xy, and y squared. You represent it like that. And that's exactly the spec of f of u vw divided by uw minus vq. And now let's look at the w orbit of these weights. So we have 2, 1. 2, 1 can be written as 1, 0, and 1, 1. Now 1, 0 is just a standard representation, and 1, 1 is the determinant. So the 2, 1 will be representation standard tensor determinant, and 1, 1 would be just a determinant. And you realize that then sigma check, but by this picture you can see, by the picture here you can see that sigma check is generated by the mu that we were talking about. The construction would be just standard tensor determinant plus determinant. Now M rho would be the closure of the image of this mapping, G determinant of G, and determinant of G going to endomorphism of the V21, this thing, plus V11. And that is very simple to see by that identity, that this will be all the pairs G and A. G is, of course, in GL2, and A is scalar, so that determinant of G is equal to A cubed. So A, in a way, gives you a third root of this determinant of G. Now, let's go to multiplicativity. Every theory of L function requires something which we call multiplicativity. Gamma factor for parabolically induced representation and in inducing data must be the same. Now, what we're going to do here in this, before I get into Sokurski's work, is to mention the main result. The proof is you have to grind it out. It will just come out when you push it through. Now, Renner's construction that is very, agreeable with parabolic induction. Let me tell you how is that. Let me take P to be Ln. a parabolic subgroup of G, unipotent radical N, and Levy subgroup L. I like to write it in this order. Further on, I will change the reverse this thing. And we will assume L is fixed uniquely by containing T. T, remember, was the maximal torus, which gave us the toric variety that we had. Now, L is in itself a reductive group, and with the maximal torus T. And we can restrict rho now to L check, the L group of L, and then rho L will be that representation. It will have the same weights. Now, rho L restricted to T check, and rho to T check gives the same weights and share the same toric variety MT. The WL would be the Weyl group of L and T. And then we have the following situation. Remember, we had this W times lambda I, the orbit of lambda I under W. If that breaks up to a disjoint union of orbits of WL lambda J. So if you look at this representation V, sum of this representation V lambda I that build this monoid through Renner's construction, that will decompose to this double sum. And in it, this V lambda I restricted to L is some of these V lambda JLs. Now, when you put in this together and go through that construction, you will see that what it basically says that the monoid M rho L attached to rho L by Renner's construction, if you go through this process with Renner's, is the same as the closure of L as a subgroup of G in this endomorphism. And so M rho L, the monoid attached to rho L, is the same as mu of L closure. So this construction agrees very well with the parabolic induction. Now then we have to also check the existence of that character. So remember we had a character nu from G to Gm, and then we have nu L, nu restricted to L. Nu check and nu L check both takes values inside the centers of G check and L check. And then we have this diagram. And as a result, rho L composed with nu L check will be just a identity, Z times identity. So it behaves the way we want it. Now, to get the correct normalization, remember I said you have to have a shift because the L function will not happen on the nose. We have to see this shift, eta G and lambda. Again, eta G is half the sum of the positive roots. We have chosen a Borel for that. Lambda is highest weight of rho. And for rho L, it may not be irreducible, so there will be lambda 1 all the way to lambda R as the highest weight of irreducible constituents. Without loss of generality, we may assume lambda 1 is equal to lambda, and then we can take eta L on the sum of these things as the shift. Now, this will allow us to define these two characters, lambda G and rho. So that would be the determinant that we had, remember, to the two eta G and lambda, and then delta L and rho L would be determinant again to 2 eta L times plus some of these things. That's the candidate for rho L. And then I'll define this character rho GL, the ratio of these things. Nu GL rho is equal to delta G rho to delta L rho L. This is the correcting factor that we will be using. Now, this P, and remember this parabolic that we had, I'm not going to write it as NL as I'm going to be using it in the next definition. Rho P will be the modulus character. Remember, there is no dependence on rho here. Then we define what I call Harish-Chandra transform of the particular time. It's first of all, we define the standard Harish-Chandra. So that's phi to phi P. It's a map from CC infinity of G of F to CC infinity of L of F. It's defined by this standard formula. And this will be changing to the positive if I change the order of N and L by virtue of change of variables. Then we define rho Harish-Chandra transform. All right, let's write it as rho HC. You just take this, the Harish-Chandra transform, and multiply by this, the correcting factor, nu 1/2 GL. Be careful, this is not really a scalar. So you have to be be careful with it when you go through this process. Now remember that in the case of unramified ones, the Harish-Chandra transform is nothing but Satake transform. Now, let's just assume that the conjectural kernel, K rho, will give the gamma factor. So in this way, that K rho of convolved with F times nu to the S A that G is equal to gamma of S pi rho times nu to the S plus A to G and lambda. And the same thing for the parabolic P and L that we have. Now, K rho is a map from smooth functions of compact support on G of F to subspace of C infinity of G of F. This is a delicate thing. I mean, you have to know what Kf is, that K rho is, and then K rho L is similarly C infinity of L of F going to C infinity of L of F. Now, we assume that this K rho and K rho L commute with rho Harish-Chandra transform, which remember we defined phi rho. So this means that if you take K rho at phi and then apply the rho Harish-Chandra transform, is the same as if you take phi rho of P, the Harish-Chandra transform, and compose it with the kernel giving you rho L. Or mainly this commutative diagram holds. So K rho up there, K rho L down there, and then they commute. Now, this, by the nature of assumption, shows that this rho Harish-Chandra transform has to send K rho of C infinity of GF to K rho L of C infinity of LF. And remember, these are just subspaces in here. You never expect that the Schwartz space to be just functions of compact support. And then we now can define for our purposes, for the proof, eventually when a theory is developed, these things has to be sitting there, that S rho of G is equal to, denotes S rho of GF, and S rho of L is S rho L of LF. I mean, then they are defined as follows. So S rho of G is defined to be C infinity of G of F plus this K rho, the kernel, or the Fourier transform at C infinity of G of F. This will be inside, the sum will be inside C infinity of G of F, and S rho L of L the same way is C infinity of L of F composed plus this sum. That's again sitting in here. And remember that the phi to phi P rho sends C infinity of GF into C infinity of LF. And therefore, we have that this map sends K rho of C infinity of GF to K rho L of C infinity of LF. Now, so we conclude that the Harish-Chandra transform sends S rho of G to S rho of L. And in fact, that commutativity holds for all the functions in S rho of G and S rho of L. So now this is the way Braverman-Kazhdan defined the spaces of their Schwartz function. And I think this is his philosophy. I think J.S. Getz told me that you can extend these things to the Archimedean ones. So there is this seems to be a quite natural assumption to make, that these are the space of Schwartz functions. Now, what is the general multiplicativity? Now, P equal to an L is the parabolic subgroup of G that we have. Levy equal to L, and we have fixed it in such a way that it contains the T, the maximal split, or the maximal torus that we had. And defined for us the monoid, I mean the toric variety, and built on that we define M. And then let's take sigma, an irreducible admissible representation of L of F, and let rho L be a finite dimensional complex representation of G check, and rho L just a restriction to L check. And let's look at the gamma factor defined by S, sigma, and rho L, and gamma of S induced sigma from Pk to Gk to be the gamma factor attached to this. Of course, this induced representation is not irreducible, so we have to choose a constituent. The good thing is that no matter what constituent you choose, you will have the same gamma factors, and it's in virtue of this multiplicity statement. It tells you that the gamma factor of the inducing data should be the same as the gamma factor of the data. Again, I mentioned this down here, that this induced representation is not irreducible, and the gamma factor is defined to be that of any irreducible constituent. And the equality itself already tells you that it doesn't depend which one you choose. The multiplicative is very, I mean, in some approaches, it's very natural because of the nature of the generality of the approach. On the other hand, in the case of Rankin-Selberg, which is a very broad set of of cases that they treat tremendous amount of cases, and it is pretty hard. I mean, the examples of are the work of Jacquet, Piatetsky, Shapiro, and Shalaika in that 1984 American journal, and also the work of Sudri. Several of Sudri's papers proves this in the case of SO2 and +1 and the classical groups. On the other hand, in the Langdon-Shahidi method, this is natural because it just comes from the natural property of the method, and that's the multiplicativity of intertwining operators. And as you can see in this method, it's also general because of the general form of the integral representation. So the main result is the following: sigma an irreducible admissible representation of L of F. Now let pi be an irreducible constituent inside the induced representation of sigma from P of F to G of F. Now let rho be an irreducible finite dimensional complex representation of G check and restrict it to L check, call it rho L. Assume that commutativity holds and assume that the kernel of the Fourier transform is invariant under K conjugation, but that has to be standard because it is expected, because it is invariant under the int G of the K rho. So K rho is invariant under conjugation, and then the statement is that gamma of S pi rho is the same as the gamma of S sigma rho L. Now this clearly reduces the problem of computing these gamma factors to supercuspidals. So that's what I'm going to now explain. This is part of Sokurski's thesis. So he computes this kernel for some of these interesting representations. Let me take now G equal to GL2. He can do some of these for GLN, but let's just take that one. And let us just look at the tame supercuspidals, those that Howe parameterized. So it's basically machinery of Howe and Bushnell-Kutzko. And a good reference for the things that are in here in this book of Bushnell and Henniard, which is a very nice book to read. So these are defined by quadratic extensions of the base field K. Now you would need a chain of OK modules. So let me take L to denote a chain. So L is equal to, it runs from L0, L1, so on, just a formulation. This thing would have to be pi K period. Pi is a uniformizing parameter inside the field, inside K. And basically pi K of Lj, Li in one of these parts, one of these elements in the chain should be L of I plus E. Now this is a quadratic extension, so the E is going to be the ramification degree. E is given to be equal to 1 or 2. And it is then the corresponding chains are in the unramified case are OK plus OK, PK plus PK. These going to be, these are going to be fixed under the action of the particular subgroup of G, which is very important. And then when E is equal to 2, this is the ramified case, then the chain is just OK plus OK, PK plus OK, PK plus PK. You can see that then the pi K will act according to this period 2. Now we realize GL2 of K, E is a two-dimensional vector space over K, and we can realize GL2 of K as automorphisms of K automorphisms of E. And the lattice, let L be a lattice chain of OK according to this shape that I gave you above. Now you take the stabilizer. This is really like Broad-Titz kind of thing. You take the stabilizer of this chain, and let's the stabilizer of L in this GL2 of K. Let's denote it by U. Depending on ramified or ramified, it's either GL2 of OK or I of OK, the standard Algebraic subgroup of OK. Now there's a standard filtration of this U to sub OK modules, and This is the kind of character which, I mean, this is the admissible characters that Howe used to define these this 10 ramified supercuspidals. So C is a character of E star. It is admissible if it doesn't factor through the norm, and if you take C and restrict it to U1 of E. U1 of E is just 1 plus PE. The P is maximal ideal inside the ring of integers of E. And if it factors through this, if the norm factors through this, then E over K must be unramified. So this is definition of admissible. Then there's a way of building this. Let me just remind you that depth of character is the minimum integer n, so such that C restricted to 1 plus PE to the n is equal to 1. We parameterize supercuspidals by admissible pairs. I'm sorry, I forgot to give you chances to ask questions, but is there any questions before I go deep further into this? Okay. Now we may parameterize supercuspidals by these admissible pairs E, K, C for an admissible character and of depth n. This is Howe and Bushnell-Kutzko. Then you construct through this way, I mean the way representations are defined, the monomial representations are defined. You define them to be given by this group U, I mean, and this tag C is a representation of U, and it can be extended naturally to a representation of E star times U, and then you induce from there compact induce, and this gives you the supercuspidal. So this is pretty standard old stuff in that sense. And then we plug this into the Godement-Jacquet theory. This is again in the book of Bushnell and Heniard, these things as this, in the case of standard representation, these are defined. So this Z will be, I mean, just forget about the taking the scalar matrix value, just take the representation itself. And R is 2 in this case. And then this Z is going to be equal to integral of F against pi. So this is an operator. And then let's just denote by tau equal to tau. See, the one only needs Schwartz. I mean, let's take this idempotent E tau attached to tau. So volume of U inverse times dimension of tau times characteristic function of U. And then, of course, we correct F by multiplying F on both sides by this idempotent E tau. So it takes us to the right space. And then if we restrict to this finite dimensional operator, Z of that tau tilde and tau, take them to be the same. And this Z is going to be equal to this. And then we let F go to the delta distribution at identity, and you pick up what epsilon is. This is the epsilon factor for at the value S minus a half. It's going to look like this. So tau or tau tilde X inverse psi of trace. So this is basically gives you the kernel. Sum is going to be equal to pi to the minus n times U. Remember, U was either it was either GL2 of OK or the ofVe subgroup, standard ofVe subgroup. Now, this leads to a Gauss sum. Tau has level n, so this integral breaks up. It becomes to a Gauss sum. So the Gauss sum, this non-abelian Gauss sum, is just defined by the, I mean, instead of a character, the standard Gauss sum is a character times the additive character. Now here it becomes the representations times the psi of the trace. And this is done over the, I mean, remember the level of the inducing character was n. So this is done over Cu, and C is just pi to the minus. It takes C to be just pi to the minus n. So this is done over this quotient. And then, of course, you have the local Lagrange. This is the coarse form of it. I mean, you need an extra character, but this is, if you start with this admissible character C and induce it all the way from WE to WF, then that will be through this, that will correspond, except for that character which is missing, that will correspond to this compactly induced representation. And so what we do, we want to do this in some non-abelian, some more interesting cases. We want to get epsilon factor in some interesting cases. Let me do it for the purposes of this talk. Let's restrict ourselves to add Q. again, as you see, if I avoid the characteristic, the residual characteristic 2, this covers everything. But in residual characteristic 2, we have those exceptional representations of Kutzko, and life is, much harder. But at least in this setting, we want to find the kernel that we have been talking about. So now we'll take representation rho equal to add cube that we discussed earlier. And then this C and pi C, when you go through this local Langlands correspondent, is going to go to the induced representation from pi C tensor pi 2C minus C. Now, sigma is the non-trivial character, non-trivial element of the Galois group of E over K. Now, this, and this will be just like this. So you put this pi C tensor pi attached to 2C minus sigma C. Those are both admissible characters. That would be a representation of GL2 cross GL2, and you extend it, you induce it to GL4. That would be the representation on GL4 that this thing goes to, and by multiplicativity, the gamma is just going to give you this. It would be, remember, I defined this thing, this G psi of tau tilde, and that's equal to this non-standard Gauss sum. Then in that case, multiplicativity tells me that you will have product of these two Gauss sums, the one for tau tilde of Xi and the one by tau tilde of 2Xi minus sigma of Xi. And then that will be a sum over tau tilde of, you put those things, you multiply those things together. That would be tau tilde of X inverse Y. You just plug the definition. And this thing and times, it will be psi of trace of X times psi of trace of Y. And then that adds up to some of these things. Now we want to go backward. We want to get the kernel. Let's go backward and write down the integral. Integral is over E star of U twice. Will be tau Xi at X inverse and tau tilde Xi at 2Xi minus sigma Xi at Y inverse and the psi of trace. Now just put them together. It's just going to look like this. So it will be integral over E star of U twice, tau Xi tilde at X inverse Y minus 2 and then sigma of Y and then psi of trace of X plus Y. Now let me put Z equal to XY squared sigma of Y inverse, i.e. the image of the following map, going from E star of U twice to E star of U sending X and Y to XY squared sigma Y inverse. Then we can write this integral up there as the tau tilde of Z inverse, and then the integral over, just look at it, it's going to be over all the pairs X and Y, and this is in E star of U, each of them, and then mu of this element is equal to Z. And that would be psi of trace of W, dW, dZ. So you clearly see that this gamma factor for the add cube is given by the convolution of this kernel against the representation. Representation is now this tau tilde of Z inverse, so it's the base representation. So given a tame supercuspidal, you can find the data, tau tilde, and you can integrate your kernel. This will be your kernel. You can integrate it over the E star of, over Cu. C, remember, is just pi to the minus n. And then this will be the kernel. So you will see that this can be expressed as an integral of this kernel over this level, Cu times Cu, which is, and C is again, just take it to be equal to pi to the minus n. Now then you will see that for every n being the level of the character, of the admissible character of Howe, and then you can define this k psi of add cube will be going Z going to the integral over this fiber mu inverse of Z of psi of trace of W dW. And mu is this thing, so this is exactly the way Engel proposed that these kernels should look like. W lies in the layer Cu times Cu. This depends on N and the lattice chain L. Now, what he has done, which is we are not going to cover here in this talk, is that you can compatibly choose these kernels over all n and all the conjugate classes of embeddings of this quadratic extension E into n2 of k to get a K psi of rho. This will be the general kernel for any, for add cube, for any represent. When I say pi tensor pi check, it's just a matrix coefficient, basically, so that when you convolve this compendium of all these kernels here, then that will give you the epsilon at rho and 1/2. Of course, I say at 1/2, you can always shift things around to get it at S. And so this means that this kernel here is really the kernel for add cube. He can do it for any odd ones. For even ones, it's more difficult. He can do it also for in cases of GLN. And this is going to be part of his thesis. Hopefully, I mean, maybe he will finish. I'm hoping he finishes this year. He wants to finish this year anyway. And hopefully, I mean, considering the situation of COVID, who knows if there are any jobs for these younger people, but I'm hoping they will be. And I expect he will do very well. I think I'll just stop here. Thank you very much. I think Dimitri.
So,
Yeah, any questions? I'm sorry.
yeah, do I understand? I just didn't get putting all in together. Do you have does he have some kind of formula for add cube for this kernel?
It's given by that integral. So this integral down here. This is the kernel.
Okay, but it depends. It seems to me
Yes.
essentially you have two different formulas.
Yes.
For a ramified and unramified case.
Yes. I mean, I think I don't know. I mean, he should be present, and I think this claim, he says that he can put them together to get a kernel. So, anything.
Okay, but very interesting to see, because in the end, the answer shouldn't depend. It should be some kind of universal function. But very interesting if you could write it in the end in a way which does not depend.
This here.
Yes.
Can you do that? Also, Kazhdan is asking if you can get a general formula.
So I still don't know if how to make it agree with the unramified case. I don't know that. I don't have the answer to that.
But how much do you know?
Sorry?
How much do you know?
I mean, we know that, we know the unramified case and we know the supercuspidal case, and in principle, it should be given by a single formula, as you say. But it's not clear from this definition that they agree, but they should.
Okay, thank you very much. Very interesting to see. Because then you can check the same formula should also work for these two residue characteristic too when you have additional supercuspidal representation. The formula should work there also. But for this, you have to write it in a form which...
Yeah, it shouldn't depend on the tameness. It's just for convenience.
Yeah. Okay. Very interesting. Thank you.
Professor Shahidi?
Yes.
So what is the main obstacle or substitute to go beyond the tameness supercuspidal representation here in this computation?
I don't think he has. I mean, this is I mean, he just this thing takes care of the non-tameness, and as Professor Kazhdan said, I mean, you have to have some formula which takes care of also unramified and takes care of something general that works also for the characteristic, residual characteristic too. So there should be a formula. I mean, the formula that I mentioned here, this one, this kernel here, is for these same supercuspidals. I mean, you have to of course put this for all of them, and then it should be a formula that takes care of the residual characteristic too. Should take care of the unramified representation and everything.
Thank you.
Sure.
Hi, Fredun. Let me ask a beginner's question. I'm not really following very carefully this stuff, which is extremely beautiful. But in this thing you have at the end, you explained earlier in your talk what the monoid was that for this add cube. And then you've given us these formulas for the kernels. But can you give us some quick idea about how these formulas here relate back to that toric variety monoid construction you had at the beginning? As I said,
it's
somehow not here, right?
Okay, I mean, it is well explained in the Engo's paper. He has a paper for
Okay, I should look at Engo. Okay.
So it is there. You can take a look.
Okay.
We are writing a paper, William and I together.
Okay.
In the case of tori, you can see. I mean, in the case of the doubling, Lapine and Rallis calculated it. Then all these things I agree with. All the calculation is done, and you will see in the case of tori, you're going to have the kernel. And tori is the one which corresponds to the toric variety. So that's an example. That's a case. I mean, that's that's a reductive group, and that's its monoid. And the integration, the kernel will really be related to that. So it is there.
I can look there. Thanks.
Sure.
Further questions, please?
Yeah. I have a question.
Please ask it.
I wrote it on the chat. Maybe you can't. Maybe you can't. I would like to ask maybe regarding a global context. Or
yeah, I mean, well, we are stuck in the local, but global context. I mean, there is these Fourier transforms are supposed to give the Poisson summation formula in the global case. And there are cases when this thing is done. I think the J. Sketz has done some for triple product or some cases of this, when there is a Poisson summation formula that works. I mean, already Kazhdan and Braverman have some cases of that. Government, and in this case, they are avoiding the boundary situation. But this paper, I mean, that does not. It includes this paper with buying you. They include the boundary situation, boundary points when Schwartz goes to the boundary, and then they really get the clear in those cases. But there is still, I mean, you have to build a good local theory. But these Fourier transforms must have first of all, they have to be, I mean, the square must be essentially themselves. So the Fourier transform applied twice has to be equal to the scalar equal to itself. And these things should have that property, but they should be also amenable to a global situation. So they should give you a Poisson summation formula, which of course will give you the global function equation and everything. Did I answer you, Ian?
yes, I have another question. You answered, thank you. I would also like to ask this part. There's a power outage here, but you discussed the additive character. At least I managed to see, and I wanted to ask if the relevant transformation rules are satisfied. I mean, when you change the character, did you check?
That thing. Well, it should be. I mean, it should work. I mean, it will affect the gamma factor, of course, and it should show up. I think it has to be checked, but that shouldn't be hard to check.
And how does this? So these factors can reproduce what the doubling factors get for the
Yes,
standard.
I have
You
checked.
said that, yes.
Yes, yeah, it does. It's like this. I mean, it's this condition, the multiplicativity, the commutativity that I discussed, is proved by the Latin and Rallis in their paper in Rallis' volume, and they have checked. This is called. You have to be careful in that. I mean, there is a lot of variable. A lot of. I mean, this delta p shows up everywhere, but it cancels, and at the end, all that remains is that. Remember, I have that delta. I define this time. All that remains is this. And this naturally remains, but this is a natural part of the Gaussian transfer. It has to be sitting there. And in the work of Lafort, you see this. You see exactly the same formula. He does it only for GL2 and some of the models. And of course, Lafort's approach is different. Lafort assumes that we know the Fourier transform and it's given by the root number, and then he builds a theory on that. And using convex theorem is open to prove the computational period. So that's another game. That's a big problem. And this is really a function of L. You have to be careful with it. When you really go through this multiplicativity, it's not that you have taken the diagram and you have multiplied by this. And this I checked, I mean, in the cases that we know it's important to notice that this is not just on a scale. Yes.
Hi, Freidun, I have a question.
Yes.
So in your talk, you were talking about a basic function in the beginning of in the first half.
Yes.
And in the last calculation, you might have mentioned it. What plays the role of a basic function in the tame supercuspidal case?
It won't be. I mean, the basic function would be for the unramified case.
It's only for the unramified.
I mean, the perfect definition of these things are given in these papers. When we leave now Springer volume, when he does the case of the doubling through this method, and you can take look at the definitions are given there. And no, that doesn't show up in the supercuspidal. That would be on ramified setting. That's exactly what should be there for the characteristic function of Mn of f. So that thing is, I mean, that it has to be defined carefully. It's an infinite sum. I mean, it's in the work of Engel. You can see it. It's an infinite sum, and this is inside of volume. It's not out. That's
okay. Thank you.
Sure.
Yeah, so I have, with your permission, another question. So the whole discussion was p-adic, right?
Yes. But I think the machinery, as I heard from Jace, a lot of these things can be done out million things. This space of Schwartz functions we can define this way. You have to put some conditions on growth and all that. But I think we can define it. So this should work for the out medium case. Although I haven't checked it yet.
So what is, if I may continue to ask, what is the future plan for this project? I mean, I understand your student.
We have to see what is. I mean, the multiplicativity reduces everything.
Right.
First of all, you have to have these kernels. You have to show they satisfy commutativity that I mentioned. So that's one thing to check. These kernels do satisfy that. And of course, William has to finish up, and as Kazhdan asked, you have to see if you have a general formula for this. That's part of it.
Oh, very nice. Very nice.
Okay, are there any further questions? I guess there were a lot of questions. Thank you very much again.
Thank you. It's my pleasure.
Okay, sorry.
Yeah, please.
Yes, I wanted to ask the whole. I was supposed to ask many more questions, but there was just an outage here, so it was very difficult for me. Most of the talk I had to fight. But yes,
so we can see.
Yes, so all the questions. Yes, so now I would like to ask, how does this work compare, or if there's a relation between this work and the work you have with Danny and Gao on covering groups? Do you have any idea?
We don't, but I mean, if they work with Danny and Fan, end up being, I mean, if this Godemont-Jacquet theory works, then that would be also part of the game. But I don't think there is anything done for covering groups. Godemont-Jacquet theory, has it been done for even covering of PLN? I don't know.
Actually, for some coverings, there is hope that it can be done under certain assumptions.
But it is not done, right?
No, no.
That's what I'm wondering. It's a good question. It's a good project. Younger guys should pick up and do things.
These are long papers. These are long papers.
Yeah, those. I mean, those are long. I know the first one is coming out in memoir, but not so case.
Mm-hmm.
It's a pleasure to work on.
All right. So next week we have a talk by Lei Zhang on Bessel Fourier coefficients and twisted automorphic descent.
Bye-bye. Thank you.
Thank you.
Thank you. I have to leave. How do I get out of here? I mute myself.